So I'm really excited next to introduce our first speaker, and that is Mohamed Omar. He's an associate professor of mathematics at Harvey Mudd College and the Joseph B. Platt Chair. His research focuses on discrete mathematics with a particular interest in applications of both linear and nonlinear algebra to the field. He came to Harvey Mudd after a postdoc at Caltech, a PhD at University of California at Davis, an undergrad and master's degree at the University of Toronto. He spent a little bit of his youth in the Toronto area, which is where I'm from. Mohamed has won many awards in his career and is the inaugural winner of the AMS Claytor Gilmer Fellowship. We're really thrilled to have him speak this morning on Chicken McNuggets. Take it away, Mohamed.
All right, thanks for the wonderful introduction. First, it would be great to assign me as a co-host so I can share my screen.
Kristen, do you mind doing that? Or Brian? Sorry, Mohamed, I can't do that myself.
No prob.
There you go.
Sorry, Mohamed, you're muted.
All right, let's try that again. All right, so before I begin speaking, I'll say a few things. First of all, I'm really happy to speak in this lovely day and gathering of the community. There are many, many familiar faces here, friends that I've seen from all different areas of my mathematical experiences. Actually, one of the speakers, Becca Thomas's, was my analysis professor during the qual time of grad school, and I see people from research, friends from teaching experiences, people from YouTube and everything. So this is really exciting. Also, a bit of information for those of you that didn't hear it, I actually am from the Toronto area. So it's especially wonderful to give this talk. So today I'm going to talk about Chicken McNuggets, which is sort of like not really what I'm going to talk about, but a great starting point, especially for a public talk like this, to get a sense of what it is that I'm talking about. So if you haven't heard of Chicken McNuggets before, they look like this. They come with dipping sauces like the barbecue sauce that's presented here. Now, you might have a lot of different emotions about this right off the bat. You might be elated and hungry. You might be grossed out by the level of processedness that's going on. Or you might be angry that I chose barbecue sauce instead of your favorite sauce, who knows? So these nuggets come in different boxes. So you might be familiar with the classic 6-piece. The 9-piece nugget is a little more evasive. You see this much more in other countries outside of the US and Canada, but they did make a presence in Canada, I think, when I was younger. And when I was younger, I remember thinking when I saw the 6 and 9-piece nugget boxes, like how many nuggets could I possibly order with combinations of these boxes? So there's also the 20-piece if you're really, really hungry, and then you could think, well, how many nuggets could you possibly have and take home with you if you had combinations of 6, 9, and 20? So let's focus first on the 6 and 9 case. So if you start with packs of 6 and 9, you might be curious as a kid, like what's possible. So you could have 6 nuggets by picking a box of 6, 9 by picking a box of 9. You can have 15 if you pick a box of 6 and a box of 9. And then you can see you get a lot of different combinations, like 6 and 9 will give you 15, 3 6-pieces will give you 18 nuggets, and then you can get 21. And you're noticing here that the numbers that are appearing are actually all the multiples of 3 that are at least 6. Right, so something interesting is going on, and you might ask sort of the question, is it possible to get all multiples of 3 starting with 6? Right, so for example, is there a strategic way to get something like 51? And you can kind of see a way to build this up actually from what's written here. And a way to see this explicitly algebraically. So if you have boxes of 6 and boxes of 9, and you decide to select X 6-piece boxes and Y 9-piece boxes, then the number of nuggets you'll have is 6x plus 9y. And so that's 3 times the quantity, 2x plus 3y. So if you can figure out a way to write every single non-negative integer that's at least 2 as a combination 2x plus 3y, where x and y are actually forced to be non-negative integers, then you've succeeded. If you have the experience of teaching maybe an intro to proof class or something like a discrete math class, you talk about how to represent every single integer as a combination of an integer combination of 2 and 3, but non-negative integers are required here. You can't have negative 2 6-piece boxes. It makes no sense. Okay, so you can kind of see a strategy for doing this. For example, if you wanted to represent an even number in this way, you could just use this portion right here. And if you want an odd number, you can pad with lots of multiples of 2 and then add 3, right? So if you wanted something like 73, just subtract 3 off of it and then have lots of 2's, 35 of them. So that's what you can do. If you want to represent a positive integer m that's greater than or equal to 2 as a non-negative integer combination of 2 and 3, if your integer m is even, divide it by 2 and then stick it in for x. Otherwise, go close to that and then let y be 1. And you're good. So this is a way to get any multiple of 3 that's at least 6 using these boxes. Okay, now what if you allow other boxes like a 20-piece, right? What's possible now? Well, this gets more interesting. Here, you're forced to have the number of nuggets be a multiple of 3, but now you have this number 20 that's not a multiple of 3, so you can start getting all types of integers. So let me show you an interesting phenomenon that happens in this situation when you have 6-piece boxes, 9-piece boxes, and 20-piece boxes. Starting with 44, you can achieve 44 by having 24 with 4 6-piece boxes and then a 20-piece. And then 45, there's a way to do that because 45 is a multiple of 15, which is 6 plus 9. You can get 46 and 47 and 48 and 49. So now if you think about this, if you can achieve all these 6 options, then you should be able to achieve any positive number of chicken nuggets beyond 44. Right? You want to achieve some very large number, start with any of these and add 6-piece boxes, right? You sort of covered all integers mod 6, so you can go and create any combination you like. And this phenomenon is not unique to the numbers 6, 9, and 10. It's actually true if you pick any box size list where the numbers listed are don't have a common divisor. If they did, then you'd be toast because you'd skip some numbers. But if you don't have common divisors, you're good. So we go here. Okay, so if you have a list of numbers that don't have a common divisor, say n1 through nk, all of these combinations we've talked about, combinations of, imagine you had you had k different box types, where the first one had n1 chicken nuggets in it, the second one had n2 chicken nuggets in it, etc. Then all the possible chicken nuggets you could get are all the non-negative integer combinations. If you know a little bit about semigroups, that's the semigroup generated by this list. And so we can write that explicitly here. Given the list S, we get the semigroup of all these non-negative combinations. And the thing that we were talking about, that eventually you're able to generate all positive integers as non-negative integer combinations of the elements in the list S. That thing has a name. It's called the Frobenius number. Well, one number, the integer just less than it, is called the Frobenius number. It's the largest positive integer not in S. So you can prove, it takes a little bit of an argument, that no matter what S is, there is a largest positive integer not in S. And if we looked at this particular semigroup that we saw before, you can generate 6, 9, 15, 20, etc. You actually can't, you can give a proof that 43 cannot be achieved as an integer combination of these three things, but everything after 44 can. We kind of saw how to do everything after 44 on the previous page. So this is one example of a statistic associated with one of these things called a semigroup. And a question in numerical semigroups typically is, if you have a particular statistic like this Frobenius number, how do you actually determine what the statistic is from the list S that you're given? In this particular situation, the question being, if you're given S, how do you determine f of S, the Frobenius number in this particular situation? There's a little bit of an answer known and not really an answer known. So we saw that the Frobenius number of this particular semigroup is 43. That's the largest positive integer we can't achieve as a non-negative integer combination of these things. If you have two generators for your semigroup, it turns out that the largest number you can't achieve is this number right over here. The product of the numbers minus their sum. And this is actually a really fun problem to assign in a discrete math course or an intro number theory course. It's a little bit involved, but you can guide people through the process. There's a little bit of a number theoretic argument why this can't work, and then a little bit of a inductive argument why it can't. We kind of saw before. But as soon as you increase the number of generators to at least 3, this question actually gets sufficiently complicated. And to give you a sense of what I mean, some of the work that's done to study this really looks at transforming the elements of your semigroup into lattice points and polytopes, and then doing some Fourier analysis on algebra that comes from the polytopes in order to be able to understand what's going on. So this question gets quite complicated quite quickly. But this is just analyzing the one statistic called the Frobenius number given your particular semigroup. Now, of course, the question is, this is like cute and all, but I mean, what really is the purpose? And in general, given a particular semigroup S generated by a bunch of numbers that are that don't have a common factor, there are a lot of different statistics. Frobenius number is an example of just one of them. that all are associated to things that seem like they're coming from geometry. So if you look at the actual names of these things, so for example, let's look at this statistic right over here. This is the list, or actually I'll look at this statistic right over here. This is the smallest number in what's called the whole set, which is something defined over here. And it seems like the name given to it is genus. The size of a minimal generating set for your semigroup is called the embedding dimension. So you might think this is associated to something topological. It turns out that's the case. So a lot of the motivation for the work in looking at particular statistics on semigroups is that they relate to a particular class of algebraic curves and the data on those curves. So personally, I don't study much of that algebraic side. I do some algebraic curve work in other things, but I don't study the corresponding algebraic curves here. But it gives us a sense that these problems are not like recreational and living in a vacuum, right? They're contextual. And there are other examples of applications of these statistics outside of the algebraic curve stuff in integer optimization particularly. Okay, so how does this actually relate to anything that I've worked on and I care about? Well, me and a couple of co-authors worked on 3 different analyses of this particular statistic on the bottom here called L of n. It's the number of ways to write a particular positive integer n as an integer combination of your generators of your semigroup. It's called the length multiset. So I'll introduce what this is, give you an intuition of what it is, and then tell you a little bit about what we discovered. So if you're given a semigroup and a whole number n, you can write n as a non-negative integer combination of the things in S, but you might be able to do that in many ways. The length set of n is the sum of the coefficients when you express n as a sum of these generators. So I want to give you an example, and then I want to actually relate it to the chicken McNugget framework that we introduced this whole concept from. So suppose you want to look at this particular semigroup, which, believe it or not, is actually called the chicken McNugget semigroup. This is like silly, but people called it that. It's a great example. It's a great example for motivating a lot of things. So it's a semigroup generated by 6, 9, and 20. So the length multiset, we write 60 in all possible ways that we can as a non-negative integer combination of the generators 6, 9, and 20. So here are the ways to do it on the left. Then we write down the coefficients and sum them up. The sum is the length multiset. So what's the intuition here? If you think about these as the allotments for the number of chicken McNuggets in each boxes, this vector here is telling you how many boxes you're using of each type. So for example, when you write 60 as this non-negative integer combination of 6, 9, and 20, the information you're encapsulating is that you need 29 pieces, or sorry, 2 9 pieces and 7 6 pieces for a total of 9 boxes altogether. So thinking about this using the McNugget analogy, the length multiset is writing down the box distribution, right? You're listing how many boxes you're using in all the particular ways that you write this number as a combination of these. All right, so for the number 60 and this particular semigroup, this is a set, but in general, this is actually a multiset. You could have maybe there's a way to write this, a particular number using 5, 5, and 2 boxes, and then maybe like 6, 4, and 2. I don't know, it depends on the generators. So what does this look like for given semigroups as your n gets large? So here are some pictures with the particular semigroup we just talked about, is the Chicken McNugget semigroup. And what we did is wrote down, or sort of drew I guess a dot list of the distribution of this length multiset with n being 2000. So we picked 2000, wrote down all the possible combinations. We also normalized things here. And the distribution sort of looks like this triangle looking graph. Okay, as you increase n, this red curve seems to be estimating the plot quite well. So there was an article that was written before this that used sort of, I would say, a bunch of relatively elementary techniques to show that if you have 3 generators, then the length multiset distribution looks like this. It goes from 1 over n3 to 1 over n1 in support, has a peak at this number right over here, has a peak at 1 over n2, and the peak value is this value right over here, some expression in n1 and n3. So one of the things we're curious about is looking at what happens when you move to arbitrarily many generators. So you can get a sense of what might happen. So here is a sort of a diagram when n is 2000 and n is 50,000, and s is this multiset, this generating set here. It's 11, 34, 35, 36. It's curved as opposed to triangular, and you notice there's a hump really early. That has to do with the fact that you're clumping 34, 35, and 36 together as generators, whereas 11 is relatively quite smaller than the rest. And then here's the sense of what things kind of look like when you have 9 generators. You can simulate what happens when n is 100,000. And you might wonder sort of what are these curves and what's happening? So the main contribution that we were able to discover is like a very explicit formula in bullet 1 of what the density of this thing looks like and what the function that sort of approximates it. So as n gets large, the picture is going to look very much like the graph of this function right over here. The support happens to be sort of the same as the support of this triangular distribution that we saw right over here. So it was between 1 over the smallest element and 1 over the largest element. And the interesting thing about this is for people who have experience with numerical linear algebra, this looks very similar to things that appear with B-splines, and that's not a coincidence. That's something that we investigate in a further paper. But the more surprising thing about this to us was the moments of this particular distribution. So if you look at the pth moment, that's the integral from 0 to 1 of t to the p f of t dt, which is used to determine things like mean and variance. It turns out that it's actually governed by evaluating a homogeneous symmetric function at different values in terms of the generators of the semigroup. A big part of this has to do with the relation between parts 1 and 2. Part 1 involved a lot of Fourier analysis, whereas in part 2, which is where I made a lot of the contributions in the work with the collaborators, was a lot of algebraic combinatorics analysis that sort of linked this function to van der Waals determinants and Schur functions. So the thing that's really surprising, I think, is that, I started off this talk sounding like I was sort of, addressing an audience of playful, curious students who just want to sort of play with interesting concepts. And all of a sudden, to get a full flushed understanding of everything, you really do need the power of a combination of um, some relatively advanced algebraic combinatorics and some deep distribution theory with Fourier analysis. Cool. So the last bit of this talk, I want to sort of talk about how I even got interested in, like I mentioned, a big part of my contributions was this stuff in part 2, which was the algebraic combinatorics piece and linking that from what was discovered in part 1. And so what I want to do is talk a little bit about my history and how I got into mathematics and how it led to me being this person who gets called on when people are stuck on algebraic combinatorics problems, and how that integrates into my life as a member of the LGBTQ plus community. So, I guess I have something to say before that, which is a few of the consequences of this moment stuff is you can figure out mean, variance, min and max, and number of factorizations, all explicitly in terms of the generators as a consequence of this stuff. Anyway, I kind of mentioned that before. It's kind of cool. So like I mentioned, I'm from the Toronto area. I actually grew up in the city proper. Well, I guess it wasn't the city proper then, it was North York. But I went to high school in the suburbs, and I went to this school right over here, Ajax High School. And there I really started doing math as recreation, but it was also really an escape for me. I had a really, really tumultuous coming out process. And for me, math provided this like opportunity to dive deeply into uh, interesting, fascinating problems in a land that sort of wasn't attacking me. So it really became honestly a way for me to sort of detached in a sense, but at the same time, I actually enjoyed what I was doing. And it led me, I think that experience led me to wanting to become a math major, which I did. I went to the University of Waterloo. And the University of Waterloo is known for having a combinatorics and optimization department. So as an undergrad, I was able to take over 10 courses in graph theory and enumerative combinatorics. So by the time I got to grad school, I had a lot of experience with this stuff and interest. And it was natural for me to sort of go that route. And I think one of the things that was really vital for supporting me while I was actually there was transitioning from mathematics as sort of like a tool to escape what was going on in high school to it being sort of a professional part of my life while allowing me being gay to like thrive as another part of my life. And that happened a lot really because of the Glow Center, which I don't actually know if it's still there. I think it is. But at the University of Waterloo is the LGBTQ plus organization that really fostered a sense of community, mental health, and well-being. And I think really my experiences through the Glow Center made a massive difference in me being able to sort of get through university in one mentally well piece. And without that, I don't think I would have continued on with this career whatsoever. So that gives you a sense of some of the history and a little bit of this fun project that I worked on. So now that we're done eating these nuggets, thank you.